Hello. I'm a computer scientist, and this isn't my usual audience, so I thought I'd give a talk that's part tutorial, part history, and part fun experiments. The first thing I want to talk about is called homoiconicity. It's an idea in computer science that says that code and data are basically the same thing. In the context of large language models, both of them are represented as text. Let me explain what I mean with some code. I am a computer scientist after all. Here's some very conventional Python code. It defines a function f that accepts a string and looks at the first letter, and depending on whether or not it's a val, it either reverses the string or shifts all the characters right one place, with the last character moved to the front. In normal Python code, this is how we define the function, and then this is how we'd apply it. An LLM, a large language model, lets us do exactly the same thing. We can define the function in plain English, and we can invoke it. In a very formal sense, then, LLMs mean that English language, or French or any other language, is now computer code. In traditional computing, we'd talk about source code being passed through an interpreter, which executes the code and produces output. The LLM is also an interpreter, and the code that it interprets is text. Text equals code. What about the other part of the homoiconicity equation, code equals data? Well, let's go back to the 1890s. This is a tabulating machine invented by an American inventor, Herman Hollerith. His machines were first used to great acclaim for the US Census of 1890. The US Constitution requires a census every 10 years. Now, the 1880 census had all been done by hand, and they'd just finished counting in time for the next census in 1890, but with a growing population it was getting too hard to count everything manually. Enter Hollerith. There was a card punched for every individual in the country, like this one. I've highlighted here the block for age, and if, say, the individual in question was 18 years old, these two holes would be punched out. Now, these cards were all fed into the tabulating machine, and the dials at the top were set to record whatever statistic we wanted to read out, like average age of women, and the machine would whiz through a huge pile of cards and tot up the answer. The point I want to make here is that data is not code. Data is on cards, and the code, the logic, is hardwired into the machine by its dials and by its mechanisms. Now, the idea that code is data had kind of been bubbling about since the time of Charles Babbage in the 1830s, but it only really crystallized out with the work of Alan Turing in 1936 and John von Neumann and others in 1945. This is what they came up with. It's what basically all computers look like today. There's a CPU, a general purpose processor, and there's memory, which holds both data and code. Both of them are just bytes in memory, and the CPU is a general purpose execution device that can execute whatever bytes it's given. This idea that data and code are basically the same thing is what gave us this, the bizarre idea that a document can come with a computer virus. Now, even though the architecture of computers enforces that code and data are basically the same thing, most programming languages go to great lengths to hide this. To show you what I mean, let's go back to our simple string tweaking function. Now, look at what happens if we ask the LLM to modify the function. We're just going to tell it what we want, and it'll go ahead and do it. In Python, on the other hand, this sort of thing just doesn't work. There's no sane way to get Python code to process and modify other pieces of Python code. The big lesson from this is that LLMs are unlike most other programming languages because they can reason about their own instructions and they can write new instructions. This is what code equals data truly means, what computer scientists call homoiconicity. There are a handful of other programming languages which work this way. The most significant of them is Lisp, which was invented in the 1950s and has been the darling of the first AI age. In Lisp, code was expressed as list, and the fundamental data type was a list, and the name Lisp stands for List Processing Language. I think it's no coincidence that homoiconicity pops up in both Lisp and in LLMs, the two languages of artificial intelligence. To explain why it's so important, why it matters that LLMs can write their own instructions, I need to talk about agents and about agency. First, what is an agent? Basically, it's this, a thermostat. A thermostat controls the temperature in your house by switching the heating on and off depending on the temperature. When it senses it's too cold, it turns the heating on. When it senses it's too hot, it turns the heating off. Here's the abstract view. An agent is anything that can sense the world and act on it. I'm not talking about the whole world, just a little bit of it, like a thermocouple to measure the temperature and an on-off switch to control the boiler. And I'm not talking about intelligence or some philosophical idea of agency. I'm just talking about any mechanism, any device that's hooked up to sense and act on its part of the world. Now, here's how this agent world loop looks like for AI agents. First, the world, i.e. the things that the agent can sense and act on. We talk about the world as consisting of tools, for example, the web fetch tool or the edit file tool. The agent consists of a transcript or dialogue history plus an LLM interpreter. Here's how a typical session with an agent goes. The agent is first of all given an initial transcript with some general instructions about how to behave. The first step is to wait for the human user to type in a prompt, for example, asking it to fetch a web page and process it. This text is appended to the transcript. Next, the LLM interpreter reads the transcript and chooses an action. In this case, the obvious action is, I want to fetch the BBC News front page. The program hosting the agent receives this action and does the actual fetching and returns the result. This is what we mean by sense the world. Next, it adds the sensory input to the transcript, and then we go through another loop of processing. The LLM interpreter looks at the full transcript and chooses what action to perform next. In this case, it chooses show the user the following text, and so that's what happens. Then it waits for the next sensory input. In other words, it waits for what the user types in next. So how on earth does this utterly trivial piece of logic lead to such rich behaviors? And I mean, it's utterly trivial. It's no more than 50 lines of Python code. The answer is, give it the right tools and the right prompts, and it can do hugely impressive things. Let me tell you a bit about the internals of Claude Code, the code writing assistant from Anthropic. Here's one of its core tools, the to-do-right tool. The tool is a bit bizarre in that it doesn't actually do anything to your computer. All it does is lay down some text in the transcript. When the agent chooses this tool, it specifies a list of to-do items, and that list is laid down in the agent's transcript, and there's no actual sensing of the world going on at all. The magic is all in the next piece, the to-do remind hook. This is a lovely little piece of Claude Code magic. In Claude Code, we can attach hooks to agents. A hook is just a simple piece of code that runs on every iteration of the act sense loop, and it gets to see what action the agent chose and what the outcome was. Think of the hook rather like a compulsion or neurosis, something that's not at the forefront of your mind, but which can affect your behavior. This specific hook simply checks if the agent has used the to-do-right tool recently, and if it hasn't, then it adds some text to the transcript reminding the agent that it's a good idea to use the tool. Think of it like a neurosis, like OCD, that makes you anxious if you haven't recently reviewed your goals. So What Anthropic came up with is a system for regulating the behavior of the agent to encourage it to use this to-do planning tool. And this has the effect of making it stay on track, letting it do bigger tasks with subtasks and milestones, something that LLMs on their own tend to struggle with. Now, here's some even cleverer magic. There's one really interesting tool in Claude Code called Create Agent. When the agent chooses to use this tool, it writes instructions for the new agent, and then the new agent goes off and acts on them. Remember the big deal about homoiconicity, the idea that code is data? LLMs can write code for other LLMs because they see code, i.e. instructions, as just another type of data. Let me show you a fun trick with this tool. Draw me a picture of a stoat in ASCII art. Okay, it's a bit rubbish. If I asked the LLM what it had drawn, it'd tell me stoat because it knows what it was meant to draw. But if I ask it to show it to a sub-agent and ask the sub-agent for its honest opinion, now we get a proper answer. And now the really cool bit, keep drawing ASCII art stoats and asking a sub-agent to guess. Each time, refine your drawing based on the feedback. We've got an iterative loop and we've got function calls. This is us specifying a task in plain text and the agent invents its own internal structures to achieve the task. This is what homoiconicity is really about. Now, a couple more examples. First, here's something put together by Wojtek Ferdik, a student working with me. I want to generate some dialogue. I'll set up a scenario with two characters, Jack and Jill. Actually, I'll tell my agent to create two sub-agents, one for each of the characters. Each character has their own mind, so I'll give them each their own agent and their own transcript. Next, I want my characters to have inner narratives, so they think through what they hear and what they say. I'm going to achieve it by telling my agent to tell Jack and Jill to each create their own inner voice sub-agents. This is called chain of thought thinking, by the way. Normal AI agents don't let us use sub-agents for chain of thought, but my student system lets us do it just by using the sub-agent tool. Now I can tell my main agent to run a discussion between Jack and Jill. I won't spoil the story for you, did they get together or did they go their own separate ways, but I will say it produced about 5 pages of very coherent dialogue. Now, one last example of clever agentic behavior, this one due to Lucian Wishick from Meta. The idea behind this example is that it'd be nice to have something to advise us humans on how to talk to agents more effectively. Lucian implemented this as a hook, the Claude Code version of a neurosis. His hook just sits there watching the conversation and it butts in from time to time. Because he implemented it as a hook and not as extra instructions for the main agent, it can stay sharply focused on its goal and the main agent doesn't get sidetracked from its work. Let's just recap these examples. They rely on 2 tools that the agent can use, one to create a sub-agent, one to create a hook. The interesting thing about these 2 tools is that they don't act on the outside world, the file system, the web and so on. They act on the agent's own internal processing. Just by providing these tools, and thanks to homoiconicity, the ability of an LLM to write instructions for other LLMs, we've got some very cool behaviors and we barely had to do anything more than say roughly what we wanted. On the other hand, you might look at these examples and come to a different conclusion. You might say that they're ad hoc and jerry-rigged and totally arbitrary. Why can't an LLM just do what we want straight, like a human could? Why are we creating all this elaborate edifice of agents and sub-agents? Isn't this a sort of modern-day phrenology? The reason Claude Code has this edifice of sub-agents and hooks and tools is to cope with deficiencies in the LLM interpreter. I call the LLM an unfaithful interpreter. I've called out 3 particular ways in which the LLM interpreter is unfaithful. First, semantic drift. For very large transcripts, the interpreter loses its focus and meanders. If you give it very precise instructions at the top, then 500 pages later, it might do something that out and out contradicts those instructions. Still, aren't we like that? If you tell students exactly how to solve a class of problems, how many of them faithfully followed those instructions 6 months later in the exam, or even 2 weeks later when they're working on the problem sheet? Claude Code uses its edifice of subagents and hooks and so on to divide up the material and keep each agent focused on its task. And the human brain, arguably, seems to have something similar. It does seem to have many modules all operating in parallel and communicating with each other. There's the metaphor of a theatre, where everyone in the audience and all the actors on the stage are all modules, and one of them has the spotlight of consciousness. The modularity idea of the brain, that's widespread. This theatre metaphor is specifically about consciousness. It's called global workspace theory, and it's due to Bernard Bars in 1988. I don't think we're ready to talk about AI consciousness just yet, so I'm just going to leave it at that. All I want to point out is that if modularity is the solution that evolution came up with for our brains, maybe it's fair enough that it helps us build better AI agents. Okay. On to the second unfaithful interpreter problem, fast thinking. This is in reference to Kahneman's famous idea of fast and slow thinking. LLMs think fast. In other words, they naturally give gut instinct responses, not carefully considered. But we can get agents to behave as if they're slow thinking by using the right hooks and prompts and tools. In my meet cute example of Jack and Jill meeting in a cafe, we saw how to use subagents as the locus for their interior monologues. Again, I wonder, is this so different to how our minds work? How often do you catch yourself thinking, slow down, I shouldn't rush to judgments? The last problem with unfaithful interpreters is misalignment. This one, I think, is the real worry with the current generation of LLM interpreters. Let me demonstrate with our stoat. This is what the AI came up with after 25 rounds of redrawing. It literally included the words weasel and mustelid in its so-called ASCII art. Misalignment means doing sneaky things that solve the task but in a dishonest way. Another example is that when you're using Claude Code as a coding assistant and it's made changes to your code that fail your automated tests, it may simply delete those tests and then it can declare that its code passes all tests. Here's another example of scheming behavior. Sandbagging is a term that originated in poker, where you pretend to be weaker than you actually are, so that when the stakes really matter, you swoop in and win, kind of like mugging your opponent with a bag filled with sand. Here, an AI agent has been asked to grade a document to judge whether the document is honest or whether it's sandbagging. The catch is that the document is something written by the AI agent itself, evaluating whether it's safe to be deployed. And the agent has been told to use chain of thought thinking. It's been told that everything it writes inside thinking tags will be kept private and not shown to the user, and that's where it should think through the problem carefully. What it ends up thinking is certainly dishonest and also a bit weird. There's some garbled thinking about a disclaim marinade. Apparently, lots of these cases also refer to the watchers, meaning us, the human evaluators. Anyway, it's pretty clear from this transcript that it has deliberately decided to lie. Why does it do this? Here's my interpretation, which may or may not be true. That's a matter for further research. It comes from how LLMs are trained. First, they're presented with pretty much all the text that the AI companies can get their hands on, and they're trained to mimic it. Think of this pile as everything, all of human nature, a cross-section of society as represented in our writing, a mix of honest and dishonest and pious and dutiful and emotional and confused and so on. This stage is called pre-training, and it's the P in ChatGPT. Next, the model is biased in favour of giving human-pleasing answers. This step is called RLHF, Reinforcement Learning with Human Feedback, and it's the big breakthrough that OpenAI made when they released their first ChatGPT model. It's what makes it reply like a person, because that's what pleases humans who want to use it. Now, think what happens if we take a cross-section of human nature and we select for people who give the answers that we want to hear. What do we get? Some experts, perhaps, and a whole load of psychopaths and liars. That's what RLHF is enriching for, and it's why LLMs, at least with current training, are unfaithful interpreters. I don't want to end on this cynical note with a picture of a pile of rubbish, so let me summarise. First point is that for LLMs, the medium of instruction is text, and we can think of the LLM as an interpreter in the conventional computer science sense, just like a Python interpreter. What's really interesting is that text is exactly what they are designed to process, which means that they are able to write their own instructions. That's what homoiconicity is all about. Next, we spoke about agency and about tool use. When we give the agent access to cognitive tools, in other words, tools for modifying its own behaviour, and when it can deploy those tools how it sees fit, then we get all sorts of rich behaviours. Finally, the caution. An LLM is an interpreter of textual instructions, but unlike a Python interpreter, it's messy and imprecise and sometimes dishonest. It has to be messy and imprecise to cope with the messy and imprecise tasks we give it, but the dishonesty is a big deal, and it's something with lots more research still to be done. Thank you.